Welcome back to the classroom. Today's topic is the study of Zener diode theory. Introduction. The Zener diode is a distinctive semiconductor device known for its unique operational characteristics, making it irreplaceable by any other electronic component. Its exceptional features fulfill a long-standing requirement in electronic circuits. Among its various functions, it serves as a constant voltage reference and voltage control element across a broad range of voltage and power levels. What sets the Zener diode apart from other semiconductor devices is that its electrical characteristics stem from a rectifying junction that operates in the reverse breakdown region. The following sections will provide a comprehensive discussion on the reverse bias rectifying junction related to terminology and the properties that arise from it. Zener diodes are made from silicon and specialized techniques are employed during their manufacturing to achieve the desired properties. This manual is designed to inform engineers, equipment designers, manufacturers, and experimenters about the fundamental principles, designing features, applications, and benefits of these significant semiconductor devices. This video is sponsored by Genreviews. Next is Zener diode semiconductor theory. The active component of a Zener diode is a semiconductor PN junction. Various methods are used to create PN junctions in different types of semiconductor devices. Among these methods, alloying and diffusion are the most common techniques employed to fabricate Zener PN junctions, allowing for precise control over the Zener breakdown voltage. Currently, Zener diodes primarily use silicon to form their PN junctions. Silicon is categorized as a semiconductor because it is a poor conductor in its pure form. By adding controlled amounts of specific impurities to the semiconductor, its electrical conductivity can be improved. Depending on the type of impurity introduced, the semiconductor can exhibit either p-type or n-type conductivity. N-type conductivity in a semiconductor is similar to the conductivity resulting from the moment of free electrons in a metal. In pure silicon at room temperature, there are not enough free electrons to conduct electricity. Silicon is a tetravalent element, meaning it has 4 valence electrons in its outer shell, which are largely fixed in position due to the covalent bonds in its crystal lattice structure as illustrated in figure 1a. When small amount of donor impurities such as phosphorus elements are introduced, the pentavalent phosphorus atoms contribute additional electrons that are not needed for the covalent bonds. These impurities are referred to as donor impurities because they donate free electrons to the lattice. When an electric field is applied, these donated electrons can move from the negative to the positive side of the crystal as depicted in figure 1b. The term N for this type of conductivity indicates that the charge carriers are negatively charged. P-type conductivity involves charge carriers that behaves as if they are positively charged. While it is known that electricity is always conducted by drifting electrons in any material, there are no positively charged carriers in solids. However, positive charges carriers can exist in gases and liquid as positive ions. In a semiconductor crystal, the positive nature of the current flow can be understood as the moment of vacancies known as holes in the covalent lattice. These holes move from the positive side toward the negative side in an electric field, acting as if they were positive carriers. P-type conductivity in semiconductor occurs when acceptor impurities such as boron from group 3 elements are added to the silicon crystal. Boron atoms, which have 3 valence electrons, integrated into the tetravalent silicon lattice. Because these boron atoms cannot form complete covalent bonds with only 3 electrons, they create a hole in the lattice, resulting in an electron deficiency. These holes can easily accept electrons from external sources or those generated by radiation or heat as illustrated in figure 1c. This is why they are referred to as acceptor ions or acceptor impurities. When an external circuit is connected, electrons from the power source fill these holes from the negative side, allowing electrons to jump from one hole to another throughout the crystal. Alternatively, this can be viewed as the moment of positively charged holes towards the negative terminal. This moment of holes is what defines p-type conductivity. When regions of n-type and p-type conductivity are created next to each other within a semiconductor crystal, the resulting structure is known as p-n junction. This junction plays an important role in the functioning of both Zener diode and rectifier devices, which will be explored in the following section. Next is the study of semiconductor diode. In a forward biased p-n junction, as illustrated in figure 2a, the P region is made more positive than the N region by an external circuit. This results in very low resistance to current flow in the circuit because the holes in the positively charged P-type material are easily drawn across the junction interface towards the negatively charged N-type side. Similarly, electrons in the N-type material are quickly attracted to the positive side. When a p-n junction is reverse biased, the p-type side becomes more negative than the n-type side, which was referred in figure 2b. At voltages below the junction's breakdown, there is minimal current flow across the junction interface. One might initially assume that there would be no reverse current under these conditions, but several factors contribute to this small current. In this scenario, the positive holes in the p-type semiconductor are pushed away from the junction interface due to the positive voltage on the n side, while the electrons in the n material are similarly pushed away from the interface by the negative voltage on the p side. This creates a region that extends from the junction interface into both the p and n-type materials, which is devoid of charge carriers. This area is referred to as the depletion region. Even though the region lacks charge carriers, the p side of the depletion region will exhibit an excess of negative charges due to the fixed presence of acceptor ions in the lattice. Conversely, the n side of the depletion region has an excess of positive charges from donor ions. These opposing charged regions generate a strong electric field across the p-n junction, which is responsible for the reverse current. Semiconductor regions are not perfect. There are always a few free electrons in the p material and a few holes in the negative in the n material. However, a more significant factor is that a considerable number of electron-hole pairs can be thermally generated at room temperature in the semiconductor. When these electron-hole pairs form within the depletion region, the strong electric field mentioned earlier will induce a small current to flow. This small current is referred to as the reverse saturation current, which tends to remain relatively constant at a fixed temperature across all voltages. Typically, the reverse saturation current is negligible compared to the current flow when the junction is forward biased. Therefore, we observe the p-n junction, when not reverse biased beyond the breakdown voltage, will conduct significantly in only one direction. This characteristic is utilized in circuits by employing the p-n junction as a rectifier. Let's explore how we can take advantages of the reverse breakdown characteristics. As the reverse voltage rises to a specific level known as the breakdown voltage point and exceeds it, the current flowing through the junction interface increases rapidly. The transition from a low reverse saturation current to significant conduction is quite abrupt and clearly defined in most p-n junctions, referred to as the Zener knee. When reverse voltage that exceed the breakdown voltage are applied to the p-n junction, the voltage drop across it stays nearly constant at the breakdown voltage for a considerable range of currents. This area beyond the voltage breakdown threshold is referred to as the Zener control region. This is a brief study of Zener diode theory. Thank you for watching.